Hello, my name is Monique Martinez, and I am majoring in biomedical engineering, and I am the team lead of Team 21038.
My name is Abdurrahman Al-Kamri. I am majoring in industrial engineering and I am the procurement lead.
Hi, my name is Alexandra Heald and I am majoring in biomedical engineering.
My name is Federico Peterson and I'm also majoring in biomedical engineering.
My name is Joshua Somerville and I am majoring in biomedical engineering.
My name is Juan Guerrero and I am majoring in mechanical engineering.
All members contributed to the project Vertical Flow Immunoassay platform for low resource settings. The Center for Applied Nanobioscience and Medicine developed a novel paper-based vertical flow immunoassay, otherwise known as a VFI, capable of detecting targeted disease biomarkers.
The current platform only functions in a laboratory setting with an electronic syringe pump and a desktop scanner. The goal then was to evolve the platform from its laboratory setting for use in low resource settings with limited access power.
The functional requirements then were to design and fabricate a system with a mechanical syringe actuator, a cell phone camera integration element for imaging, and a more ergonomic VFI design in addition to being lightweight and durable.
To begin using the platform, the mechanical actuator is set to an upward ready position by the user. A filled syringe already attached to the VFI is then placed into the designated spot within the actuator. User then activates the actuator and allows it to depress the syringe fully, which pushes liquid through the VFI for the needed amount of time. Once done, the user resets the actuator and removes the syringe from the holding position.
The VFI can then be screwed off the lower lock of the syringe and screwed into the camera-compatible element for imaging. When attached to the iPhone, the user can take a photo of the internal paper membrane for future analysis and eventual diagnosis.
Overall, our system contains 3 subsystems, which include subsystem 1, the case and syringe mechanical actuator, subsystem 2, the ergonomic VFI, and subsystem 3, the phone camera optical imaging integration.
Within each of these 3 subsystems, there are specific system requirements. These system requirements were either tested, inspected, or analyzed using developed verification procedures to ensure verifiability of the entire system.
The subsystems are representative of the project's minimum viable products and reflect the requirements presented by our sponsor.
MVP1 is considered the mechanical actuator because it is a critical technology. The team could not begin testing the forces needed for the constant force springs or determine the size of the overall carrying case until the actuator was designed and updated appropriately. The actuator also produces the tested paper membrane that can be imaged and processed to determine if the VFI detected a certain biomarker.
Since the next major step after the mechanical actuator produced a test membrane is to take a picture of said test membrane, the team decided that MVP2 would be the cell phone integration component. This component was the second most important part of our system.
So finally, the team decided that the ergonomic VFI will be MVP3. Since this MVP is simply an attachable accessory to make handling the small VFI component with heavy working gloves easier, this component does not directly affect the process of obtaining an image of the VFI.
In terms of design, the mechanical actuator is the first component identified by the system architecture and system block diagram, and is the basis for a majority of the functional requirements and system requirements.
The design of the mechanical actuator was determined after completing a series of trade studies. The initial concept included a syringe depressing mechanism capable of increasing the force on the syringe in a stepwise manner using 2 sets of constant force springs.
The mechanical actuator was then designed and fabricated. The device was tested to ensure functionality in 0 power settings, an efficient setup time, the necessary syringe capacity, and the desired constant flow rate.
The ergonomic VFI housing is the second component identified by the system architecture, the system block diagram. The VFI housing bridges the gap between the syringe mechanical actuator and camera integration imaging element.
The design of the VFI housing was determined after completing a trade study. The initial concept included a clamshell-like design that clamps over the VFI to increase its size and usability.
The housing was then designed and fabricated. The device was tested to ensure it improved handling time and was an efficient size for use.
The last component identified by the system architecture and system block diagram is the phone camera optical imaging element.
The design of this imaging element was determined after completing a series of trade studies. The initial concept included a case attachment with a twist and locking lens component compatible with the attaching VFI.
The imaging element was then designed and fabricated. The device was tested to ensure its compatibility with an iPhone 8 rear-facing camera, center alignment, and necessary magnification.
To begin testing, the user places a syringe into the mechanical actuator. The user then twists on the VFI component already fitted with the more ergonomic housing onto the syringe. The actuator is then allowed to run and depress the syringe using the two-step latching system, forcing liquid through the internal VFI paper membrane.
Once the syringe is emptied, the user removes the VFI from the syringe using the ergonomic housing. This housing consists of two parts and screws together directly over the VFI. Once the VFI is removed from the syringe, the user can attach the component to the camera imaging element. This element is fitted into the case of the iPhone 8 and contains an attachment site for a lens component and the VFI.
When the VFI is in place over the iPhone's camera, the user opens a third-party application capable of taking a raw image of the internal paper membrane. The user is encouraged to increase the amount of light entering the internal area of the VFI by tilting the phone to a light source. The image is then taken and saved for analysis and eventual diagnosis.
The case for the whole system has a wall thickness of less than 0.5 inches, but more than 0.2 inches. The system also has a compact size, fitting into a standard size backpack. The case also exhibits enough strength and durability to function in the target low resource environments, while also running an actuation in less than 30 minutes with zero power needed at a targeted flow rate.
The VFI itself is easily handled with the ergonomic housing, allowing a user to remove the component from the mechanical actuator and attach it to the camera imaging element in less than 20 seconds, thanks to the component's almost 2-inch diameter.
Regarding the imaging portions, the camera compatible element generates a centered image of the internal VFI paper membrane. While ensuring all iPhone functionalities, the image itself is also magnified 10 times over the appropriate analysis.
Focusing on the lessons learned, one of the team's lessons centered around the Agile methodology. By taking advantage of the Agile course structure, the team was able to prototype and assess initial designs prior to fabricating a final product. These assessments allowed for useful updates and improved device functionalities.
Another lesson learned focused on machining. The team had a very limited machining experience prior to starting this project. The desire to machine parts affected almost every aspect of the project, including the budget, schedule, and part design. Any design specifically for the mechanical actuator had to be redesigned several times with machining in mind.
For the deliverables, the sponsor team will receive any and all the materials purchased.
The sponsor team will also have access to all modeled parts and the physical prototypes of all project iterations, in addition to all the documentation outlined by the course.
The sponsor team will have all the necessary materials to fabricate their own parts and replicate the design produced by the team if desired.
The designs directly reflect the team's Agile methodology and are the results of defined design and verification processes. The team was able to design, fabricate, and update all system elements to ensure proper functionalities and meeting of sponsor and mentor expectations.
The team would like to thank the sponsor team, Alan Nordquist and Dr. Jiang Wu, for their support. Additionally, the team thanks our mentor, Sharon O'Neill, for her guidance. Lastly, the team thanks you for your interest in our project. Have a great day. Goodbye.